Greetings and welcome to Distillate. In the previous class, we discussed about the ideal gas equation. The ideal gas equation is used to notate pressure, volume, number of moles, and temperature. So the equation is PV is equal to nRT, where R is the universal gas constant with three different values that we discussed depending on its units. First is 8.314 joule per mole Kelvin. Second is 0.08206 liter ATM per mole Kelvin. And the third value is 1.987 calorie per mole Kelvin. All right. Then we also discussed a few units of pressure. And I told you about the unit conversion. So when we talk about pressure, then pressure has its SI unit as Pascal. All right. Now, if we want to convert from Pascal to kilopascal, then we'll have to multiply by 10 to the power minus 3. If you want to convert from kilopascal to Pascal, then we'll have to multiply by 10 to the power 3. Similarly, if we want to convert from Pascal to ATM, then we'll have to divide by 101325. And if we have to convert from ATM to Pascal, then we'll have to multiply by 101325. Similarly, if we have to convert from Pascal to bar, then we'll have to multiply by 10 to the power minus 5. And if we have to convert from bar to Pascal, then we'll have to multiply by 10 to the power 5. All right. Then we also discussed another unit of pressure, which is millimeter of mercury. And I explained the unit conversion from millimeter of mercury to ATM. So if we want to convert something from millimeter of mercury to ATM, then we'll have to divide it by 760. And if we have to convert something from ATM to millimeter of mercury, then we'll have to multiply it by 760. This is what we studied in the previous class. Today, we are going to study about gas laws. So first of all, let's understand the concept of ideal gas. In the previous class, we discussed the ideal gas equation, and I told you that I'll be explaining you what an ideal gas is. So in this class, let me explain you that. Ideal gas is a hypothetical gas such that its molecules are situated far apart from each other, such that the interactive forces between different molecules are negligible. See what happens if we have a particular gas, or if we have any particular substance. If its molecules are close to each other, then there are certain intermolecular forces that are existing between those molecules. Okay. Hence, these intermolecular forces between molecules, they tend to divert the motion of these movements, these molecules, or they influence the motion of these molecules. All right. So for example, if this is my molecule A and this is my molecule B, and if there are intermolecular forces between A and B, significant amount of intermolecular forces, then the movement of A would definitely be influenced by the movement of B. All right. Hence, while we are dealing with an ideal gas, we assume that the molecules are so far apart that this intermolecular forces between these molecules are negligible. All right. And once we do that, then we can simply say that each molecule is independent of the other molecule. Each molecule is independent of the other molecules, and hence it can move freely. All right. It can move freely. Hence, we derive this a very easy equation, PV equals to nRT, a very simplified equation for an ideal gas. All right. Now, the question is, why do we study ideal gas equation? the reason why we study ideal gas equation, or the reason why we study this model, and this equation is actually quite a lot used in the courses that we'll be studying. We'll be using ideal gas equation quite a lot. So while we're using the ideal gas equation, let me tell you, the ideal gas equation is so much used because if we use an ideal gas equation to get a particular result, then that result is quite close to what we get using the real gas equations. For example, if we use ideal gas equation to calculate volume, and we use the real gas equation to calculate volume, and let's say we experimentally also try to determine the volume, so we'll find that these three are quite close to each other. Now, of course, the experimental value and the ideal value of volume is not that close, as real and experimental value are, but still these values are not very far apart. Suppose if this is going to be 40, then this is going to be around 42, and this is going to be around 42.3. So you can see these two are quite close, but even these two are not very far, right? So that is why an ideal gas equation gives us a basic information that, okay, we need something around this 40 plus minus 5. We need to have the volume of 40 plus minus 5. So we can have something like that. Secondly, this part we'll be dealing with in thermodynamics as well, that when the pressure is reduced, pressure is reduced to a very low level, or when the temperature is increased too much, right? At low pressure and high temperature, almost all gases at low pressure and high temperature follow ideal gas equation. All right, that is why ideal gas equation is quite important while we deal with these concepts. Okay, that is why ideal gas is taught, and that is why this equation is taught to you. Now, we'll move to certain other concepts before we go to problems. So first of all, we have partial pressure. Partial pressure in a gaseous mixture is defined as the, first of all, partial pressure will be defined in case of gaseous mixture. Okay, it would be defined in case of mixture. That is the main thing. It would be defined in case of mixture. Okay, so in a gaseous mixture, partial pressure of a component is defined as the pressure that would have been exerted by the component if it would have occupied the same volume as the mixture. Now let me explain you what this means. Let's say I have a tank or a box, and the volume of the box is 1 meter cube. All right, the volume of the box is 1 meter cube, and the pressure exerted by the gas inside the box is capital P. All right, so if I say that there is a gas A inside this box, okay, if I say that there is a gas A inside the box, and also if I say that there is another gas B inside the box, because it is a gaseous mixture inside the box. So there are two gases, gas A and gas B, a mixture of A and B. All right. So now let's say that we take another tank or another box of same volume as the original box, 1 meter cube. And then we transfer all the A. We transfer all the A from this box to this box. All right. We transfer all the A from this box to this box. All right. Then in that case, whatever would be the pressure that would be exerted by this gas A in this box, let's call it PA. That is going to be the partial pressure of A, in the mixture. Okay, because we have taken gas A from this mixture. This is partial pressure of A in the mixture. Okay. Now there's one more thing that I want to tell you. Let's say that A, let's say there are Na moles of A and Nb moles of B in this box. All right. So since we have transferred all the moles of A from this box to this box, therefore we have Na moles of A over here as well. All right. As I told you, the pressure in this box is PA, and there is no change in temperature. So the temperature here and here, it is going to be the same. That is T. Okay. It is going to be the same in both cases. In both the boxes, it is going to be the same. All right. So if we have to mathematically calculate the value of PA, then we can use ideal gas equation in this box because the volume of both the boxes is same. That is why we can say that PA into V is equal to, what is the number of moles of A in this box? Na into R into T. This is the ideal gas equation that has been applied on this box. Therefore, we can say PA is equal to NART by V. Very important. Very, very important. So basically, from here you can see that we have not changed the volume. We have only changed the number of moles, right? We have only changed the number of moles. So changing the number of moles would give us the partial pressure of the component A. Similarly, if we want to calculate the partial pressure of component B, then that is going to be equal to NBRT upon V. All right. Fine. Then we come to vapor pressure or saturation pressure. This is a concept that involves vapor-liquid equilibrium. And we have not dealt with that concept for now. So that is why I'll just explain this concept in a very simplified manner. And then when we'll cover that topic, then I'll explain this part again. All right. So for now, let's simply try to explain what vapor pressure or saturation pressure means. So assume that we have a container filled with a liquid. All right. We have a container that is filled with a liquid. Now, you know that when we have a liquid, the molecules are situated close to each other. But let's say we start reducing pressure. We start reducing pressure slowly. So if that happens, then these molecules will start moving far off from each other, right? The intermolecular distance would increase. Okay. When the pressure reduces significantly, then the intermolecular distance between various molecules would increase to such an extent that the liquid would now change into vapor or gas. Liquid would now start changing into gas. So the pressure at which the intermolecular distance between liquid molecules becomes so high that it starts to change into its gaseous state. That pressure is known as saturation pressure. All right. That pressure is known as saturation pressure. Okay. This pressure is the minimum possible pressure for a liquid. Okay. If you reduce pressure further, then it would no more be a liquid, it would be a gas. All right. If pressure is reduced to a lower level, then PAS or PA naught. This is how we denote vapor pressure, PAS or PA naught. So the pressure is reduced significantly, and if it is reduced to a value lesser than the saturation pressure, then in that case, the liquid is no longer going to exist. We'll have vapor or we'll have gas. All right. Now, let's deal with a mixture of ideal gases. So let's say if we have a mixture of n different gases, then there are two laws that would be holding for these gases. The first one is going to be Dalton's law of additive pressures, and second one is going to be Amagat's law of additive volumes. So let's understand Dalton's law. So let's assume we have a gaseous mixture containing A, B, C. All right. Now, as I told you, we can calculate the partial pressure only by changing the number of moles in the ideal gas equation. Right. Rest all can be the same. So partial pressure of A is going to be NART by V. Partial pressure of B is going to be NBRT by V. And finally, partial pressure of C is going to be NCRT by V. All right. Now, if we add the three of them, PA plus PB plus PC, then we'll get Na plus Nb plus Nc RT by V. All right. Na plus Nb plus Nc is nothing but the total number of moles that are present in this gaseous mixture. So that is equal to N total into RT by V. This is actually nothing but the total pressure, right? Hence, we can say that if we add the partial pressures of all components, we get the total pressure, right? This law is known as Dalton's law. This law is known as Dalton's law of additive pressures. Okay. Then we come to Amagat's law. Amagat's law is same as Dalton's law, just it is applicable for volumes. Just like we calculate partial pressure, similarly, we can calculate partial volume by keeping everything constant but the number of moles. So when we calculate the volume, partial volume of A, that is going to be NART by total pressure. When we calculate the partial volume of B, then we'll get NBRT by P. And when we calculate the partial volume of C, then we get NCRT by P. So when we add all of them, we get VA plus VB plus VC is equal to NA plus NB plus NC RT by P. So that is nothing but nRT by P, which is actually equal to the total volume. All right, that is equal to the total volume. Hence, we can say that if we add the partial volumes of each component, then we'll get the total volume. So in general, if we have n components, then I would say V1 plus V2 plus all volumes till n would be equal to the total volume occupied by the mixture. All right. This is known as Amagat's law of additive volumes. Then we come to this very important relation. Mole percent is equal to partial pressure percent is equal to volume percent. This is actually quite logical. Let me explain. We already know that partial pressure is nothing but number of moles of component into RT by total volume. And total pressure is equal to total moles into RT by total volume. If we divide 1 by 2, then we are going to get PA by P, which is nothing but partial pressure fraction. Right? This is nothing but partial pressure fraction. This is equal to Na by N. This is mole fraction. And then the rest terms, RT by V, it gets cancelled. So hence, we get partial pressure fraction is equal to the mole fraction. All right. That means PA by P is equal to YA, since we are taking a gaseous mixture. Okay, since we are taking a gaseous mixture. Applicable only for gaseous mixtures. Remember, this is applicable only for gaseous mixtures. Don't use this in liquid. Okay. Similar basis, we can prove that VA by V is also equal to YA. Hence, altogether we can say mole percent or mole fraction is equal to partial pressure percent or partial pressure fraction, which is equal to volume percent or volume fraction. Now, what is the use of this? So let's say I have a mixture of A and B and C. Okay. And let's say this mixture is maintained at a pressure of 1 atm. All right. Let's say the mole fraction of A is 0.2 and the mole fraction of B is 0.3. All right. I have to determine the partial pressure of C. All right. Now we have no temperature, no volume, no value of moles, nothing. We only have this much information. So how to calculate the partial pressure of component C? So we are going to use this relation. Mole fraction is equal to partial pressure fraction is equal to volume fraction, right? So we know that summation of all mole fractions is equal to 1. This we discussed in the first lecture. Therefore, I can say that YA plus YB plus YC is going to be equal to 1, which implies YC is equal to 1 minus 0.2 minus 0.3, which is 0.5. All right. Now, since mole fraction is equal to partial pressure fraction, implies we are going to write mole fraction of C is equal to partial pressure fraction of C. That is partial pressure of C upon total pressure of C. Total pressure. So that means we get PC is equal to YC into 1, that is 0.5 atm. All right. Similar basis, you can do various calculations using this particular rule. Hence, you always need to keep this in mind. Mole percent is equal to partial pressure percent is equal to volume percent. All right. Then we come to another concept, which is average molecular weight. So let's say we have a mixture of A, B, and C. This is applicable for both gases and liquid. It is applicable for both. So that is why let's take a liquid mixture where we have A, B, and C. Mole fractions of A, B, and C are XA, XB, and XC respectively. While molecular weights of A, B, and C are MA, MB, and MC. In that case, the average molecular weight for this particular mixture is going to be mole fraction of A into molecular weight of A plus mole fraction of B into molecular weight of B plus mole fraction of C into molecular weight of C. All right. In general, we can say that if we have mole fractions of all the components and molecular weights of all components, then average molecular weight can be summation of the product of mole fraction and molecular weight, average molecular weight. All right. And then we come to density of the mixture. So let's say we have a mixture and we have to calculate its density. So as I told you, density can be a property of the substance, right? So if we have A and B in the mixture, then we know density of A and we also know the density of B. But let's say we want to calculate the density of the entire mixture. So in order to do that, we are going to use this formula. Rho is equal to PM average upon RT, which can be easily derived. We can easily derive this formula using the definition of density, mass upon volume. But for now, just remember this formula. Rho is equal to PM average upon RT. This derivation is available in all the books, so you can look it up over there. Since we are done with all these concepts, let's move on to a problem. Air. So we are going to assume that air contains 21% oxygen and 79% nitrogen by volume. This is very common. You will see whenever we have a mixture, then you will always be given the components in percentages, suppose 21%, 79%, and then you will be given in the bracket by volume, by mole, or by weight. So if it is given by weight, this means that 1 kg of mixture has 0.21 kg of oxygen and 0.79 kg of nitrogen. If it is given by volume, that means 1 liter of mixture has 0.21 liter of oxygen and 0.79 liter of nitrogen. If it is given by mole, then it means that 1 mole of mixture has 0.21 moles of oxygen and 0.79 moles of nitrogen. But you also have studied before in the previous slide that mole percent is equal to partial pressure percent is equal to volume percent. Hence, if this is my volume percent of nitrogen, then this is same as mole percent of nitrogen. All right. Hence, if it is given by volume, it is understood that this means by mole. All right. So hence, we can assume 1 mole of mixture and we can say that it has 0.21 mole of oxygen and 0.79 moles of nitrogen. Okay. Temperature is given to be 298 Kelvin. Pressure is given to be 760 millimeters of mercury. So we discussed the pressure conversion, that if we have anything in millimeters of mercury, then to convert from millimeter of mercury to atm, we simply divide it by 760. So we'll get 1 atm. This is the total pressure. All right. Now you have to calculate the average molecular weight of air, partial pressure of each component, and composition of air by weight. So average molecular weight is actually quite easy. See, we have taken mole percent equals to partial pressure percent is equal to volume percent, which implies mole percent is same as volume percent. That means that nitrogen has mole fraction of 0.79 and oxygen has mole fraction of 0.21. I have written X, but this is a gas, so it should be Y. Okay, YN2 is equal to 0.79, YO2 is equal to 0.21. I didn't want you people to get confused in this formula. That is why I simply wrote X, but it's actually Y for gases. All right. So YN2 is equal to 0.79 and Y oxygen is equal to 0.21. Then we know the molecular weight of nitrogen is 14 into 2, that is 28. And the molecular weight of oxygen is 16 to the 32. Therefore, we get sigma xi mi, which is x1 m1 plus x2 m2, or y1 m1 plus y2 m2. And then we get 28.84 unit gram per mole. All right. Then the next thing that we need to calculate is the partial pressure of each component. So we know the total pressure is 1 atm. And since we know that mole percent is equal to partial pressure percent, hence the partial pressure of the ith component is equal to mole fraction of ith component into the total pressure. Okay. Therefore, we get mole fraction, partial pressure of nitrogen equals to 1 atm, that is total pressure, into mole fraction of nitrogen, that is 0.79. And similarly, we can get oxygen as 0.21. All right. Then this third part of the question asks you the composition of air by weight. So for doing this type of questions, if we need to convert anything from mole percent to weight percent, or weight percent to mole percent, there is a typical procedure for questions like this. For now, we have to convert from mole percent to weight percent. So let me tell you what we are going to do for such cases. We are going to take the basis as 100 kilomole of mixture. Okay. Since we have 100 kilomole of mixture, therefore, using mole percent, we can get moles of each component. Okay. We can get moles of each component. Let me call it component number I. Okay. So ith component's moles can be obtained by multiplying mole percent to this. All right. Then once we have got moles, let's call them Ni. Then we can multiply moles of the ith component to the molecular weight of this ith component to get mass of the ith component. Okay. And similarly, we are going to get masses of all components. All right. Therefore, total mass, from here, we get total mass is equal to summation of mass of each component. Okay. Summation of masses of each component. Then from here, we'll find the weight fraction, which is nothing but, here we'll take y dash. Y dash is equal to mass of ith component upon summation of masses of all components. All right. And if we have to calculate weight percent, that means we are going to multiply this by 100. All right. So once again, we'll first of all take basis as 100 kilomole of mixture. Then we'll get moles. From moles, we'll calculate mass. Okay, we'll multiply the moles by the molecular weight to get mass. Okay, then we'll find total mass. And then we are going to find weight fraction, which is equal to mass individual mass upon total mass. All right. So let's see what we have done in this problem. We have taken 100 kilomoles of air. Therefore, it contains 79 kilomoles of nitrogen and 21 kilomoles of oxygen. All right. Molecular weight of nitrogen is 28 kg per kilomole and 32 kg per kilomole for oxygen. Then, to calculate weight, we have multiplied the number of moles to molecular weight, which gives us 2212 kg of nitrogen and 672 kg of oxygen. Then we have added both the weights to get the total weight. This is my total weight. Then weight fraction of individual component is equal to individual weight upon total weight. Okay, so y for n2 is equal, y dash for n2 is equal to 2212 upon 2884. And similarly, we have oxygen 672 upon 2884. Hence, we have got the summation of all weight fractions equals to 1. All right. So once again, let me tell you how to convert mole percent to weight percent. First of all, we'll take basis as 100 kilomole of mixture. All right. Then using this basis and using mole percents, we are going to calculate moles. From moles, we are going to multiply these moles by molecular weights and we'll get masses. From all the masses, we are going to calculate total masses. And then we are going to get mass fraction. Mass fraction, because mass fraction is nothing but individual mass upon total mass. Okay. That's all for today. In the next video, I'll be discussing a few numerical problems with you all. And after that, we'll go ahead.